As is frequently the case, the solvent will become involved if the solvent is nucleophilic. So I have now changed the substrate and the solvent, and we're going to run another bromonium style. This, of course, will be a little bit more complicated, but it'll illustrate some important stereochemical considerations. As always, we need to draw out the Lewis structure for the reagent of interest in the first place. Bromine, once again, fits into our usual description of something that is both potentially an electrophile and a nucleophile, and the bromine has a lone pair on the electrophilic side, but of course we now also have a solvent which could be nucleophilic as well, and so what we're going to end up making, of course, is potentially a mixture of products. But let's assume for the sake of argument that what we really are after is the product that is generated when the methanol gets involved. So the first mechanistic step is going to be attack of the double bond onto the Br2 species, which causes the Br- to leave, but at the same time that this attack is happening, a pair of electrons from the bromine side comes back and makes a bond simultaneously. What that will do is create two new intermediates. So the result of all the arrows drawn is that you form two possible bromonium adducts, two different places where you have a bromine making two bonds simultaneously with two carbons. The methyl that was there before and flat is now going to be on the opposite side. So if the bromine came from the front, that pushes the methyl toward the back. If the bromine came from the back, that pushes the methyl toward the front. Both species are made, and since there's no preference in the original material, we make a 50-50 mix of both. However, we should at least draw what that looks like at the moment. So the idea here is that we originally had a flat double bond with the methyl coming toward you, and then the bromine came from the top, and the double bond attacked the bottom of the Br2 while the Br2 made a bond as well, and the other Br- floats away. So that's the idea, but the result is now a species that looks kind of like this, where we have a formal plus on this bromine, and we tend to draw it as having two actual bonds. But probably the better way of thinking about it is that you have this bromine atom, which is relatively large, that's sitting more or less on top of both carbons simultaneously, and it's donating electron density to both. But at the same time, we know that the bromine is relatively electronegative, and so though we have formally put the plus on the bromine, in reality, those electrons are going to be shared relatively unevenly and probably more toward the bromine side. So what you really want to do is think about this not as being an actual sp3-like center the way I've drawn it, but rather more as an sp2-like center where there happens to be, again, some p orbitals basically sitting right there with the bromine simultaneously donating electron density into both p orbitals, which is to say it's not a double bond anymore. It really does have some cationic character on both carbons, but at the same time, you might want to think of it as a bromine sort of sitting on top of both orbitals that were there in the first place. You should, for the purposes of bookkeeping and drawing, draw out the bromoniums this way, but sort of as a mental conception, you kind of want to think of this bromine as being able to sort of float or rotate back and forth, and it will probably spend more time donating more electron density into this particular carbon because it's the secondary carbon. That needs more electron density. It will place a little bit less electron density into the tertiary side because, again, a tertiary carbocation can better tolerate being a carbocation. So anyway, though this is going to be drawn in Lewis structure forms as though those are actual bonds, what you want to think of is them not necessarily being equal bonds to each other. So if you are going to look at this in Lewis structure terms, you would tend to think that this has a relatively small amount of delta plus at this position and a relatively large amount of delta plus at the tertiary position. That's because this is secondary, and that's because this is tertiary. Because of this fact, because of this picture, you can now imagine doing a Sn2-like reaction with the methanol. And now we once again have a choice where the methanol could either add to the tertiary-like carbon coming from the bottom, coming from the opposite side of the bromine, kicking that out, or it could do the same sort of addition to the secondary side. The answer is that it will attack the tertiary side largely because that's where the greater delta plus is. Again, the image is there's a lot of delta plus here. And though this is going to be drawn in an Sn2-like fashion, it isn't truly an Sn2, largely because, again, the right way to think of this is a bromine more or less hanging out on top of two carbocations. Really, there is a significant amount of a carbocation on the tertiary side, and rather more of an actual single bond on the secondary side. So really, you're attacking the carbocation, and there's really a bromine making a bond over on this side, and a very light bond onto the tertiary side. So this will happen via an Sn2-like process, and again, it's not truly an Sn2, but the stereochemistry stereochemical result is that of an SN2. So this is SN2-like from the perspective of the stereochemistry. It has to come from the backside of the bromine, and again, that's most vividly illustrated by this image. So the methanol adds from the backside. Naturally, what you form is going to be a methyl ether. Specifically, of course, you have a protonated methyl ether at this point. I want to point out that the methyl was back, and now it is forward and on the same side as the bromine. Specifically, the methanol has to have attacked from the backside of the bromine, so the methyl ether, protonated methyl ether, will be on the backside, away from this bromine, anti to the bromine. Another molecule of methanol, because it is a solvent, comes by and deprotonates. Your final product, when all is said and done, is going to be a pair of methyl ethers, where the methyl ether is going to be opposite, anti to the bromine, and the methyl will be on the same side as the bromine, but really that's happening because the methyl gets adjusted by this SN2-like reaction. You make this as well as the other enantiomer, plus the enantiomer of this, which is to say the result of attack bromine species on the double bond originally. So originally, the double bond could be attacked by the bromine either from the top or from the bottom. That then will lead to the enantiomer preference here. The relative stereochemistry is going to be governed by the SN2-like attack of the methanol on the backside of the carbon-bromine bond. So you make a racemic mixture, you make both the products as drawn and its enantiomer.